Hey everybody, my name is Lev Druin, and today I'll be going over the results of Lab 2, the bomb calorimeter experiment. So a little outline of what I'll go over. First, I'll just go over a little bit of theory, just to recap that. Then we'll go over the experimental procedure, just what we actually had to do in the lab. And finally, I'll go over the results and what conclusions we were able to draw. So for the theory, we can see that it's pretty much just based on the first law of thermodynamics. There's not a whole lot of complexity to it. It's based off of one equation where your Q, your heat capacitance, I cannot remember. Well, your heat capacitance of the calorimeter is equal to the, I cannot remember Q what the word is, but Q over the temperature difference, and we'll see in the next couple slides what that is, where it's just not hitting the brain right now. And for the for the capacitor, not the capacitor, the calorimeter, the total Q is just equal to the Q of the wire plus the Q of the fuel. For the apparatus, we can see that the entire calorimeter is essentially just a bucket of water with a motor stirring the water around with the bomb inside of it. The bomb is going to have two fuses coming into it, or it's going to have two electrodes coming into it with the fuses connected. The fuses are going to be touching the fuel source, and at one point, whenever you're ready, you have your temperature being read, the fuses are going to ignite the fuel. The fuel is going to heat up the water while the motor is stirring around to move the water around a bunch, and you just record the temperature difference as a function of time. This is just a little bit closer of the bomb itself. Like I said, the bomb is completely pressurized, so you're going to have to, we use oxygen. There are different calorimeters that use different things, but oxygen is by far the easiest for our purposes. So what you're going to do is, go to the next one. The process is you're going to pump the calorimeter full of oxygen. You're going to have to do this over and over to kind of pressurize it, get rid of all the extra air. I'm sorry, I skipped over one part. You got to put the fuel in, of course, first and connect the fuse, all that stuff, and then pump it full of air. Put that all together inside the calorimeter. You got to make sure all the parts are completely correct. The calorimeter that we have is actually, it's slotted a certain way so that it can only be put in one way to prevent any wiggle room. Then you start up the motor, make sure everything's completely set. You check the circuit for a continuity. You start it all up, and then you just push the red button. That makes it all actually go off, makes the bomb go off. And then you just log the data over time and turn it off once it kind of stagnates. So this is a little bit of what we got from our data. On the left is the text file that the DAC, the NDAC, whatever the program's name is, spits out. And as you can see, it has time, it has the date, and it has the temperature. And that's all that it really records. It's all that's needed for this experiment. What I did was I just transferred it over to Excel. So as you can see, the time is just in seconds. Right here, this little file right here is what I use to snip off the portions that are irrelevant, the lead-up portions where you just let the water cells room temperature, the after portions. So this is kind of irrelevant for anything except for my math, and right here you can just see the temperature. So this is the function of temperature over time. As you can see, it kind of just stagnates right along here. This is whenever we first got the motor started and just let it approach room temperature. It took about 2 minutes. Then right here to wherever we press the button, and we just watched it rise, and it quickly kind of raises itself a few degrees, and then it stagnates over there. And this is where I just chopped off the irrelevant parts. I chopped off the beginning, chopped off the end. I changed up my x-axis just for sake of clarity, seeing how long it actually went on. So these are my known fuel calculations. Up here in this table, we can see what was known before the experiment, or excuse me, before the calculations. The only thing that wasn't known before the calculations was this change in temperature, but that's something that you kind of just draw from looking at the graph. And this kind of experiment, there isn't an exact place to start or end. It's kind of just seeing what's approximately correct where it actually started, because once it starts to stagnate, you just have to say, okay, it approaches the final temperature this close, I'll call this my end temperature. And then after that, I ran through some quick little calculations. We can see that the heat of combustion, that's what I was looking for. The heat of combustion of the benzoic acid is equal to 26,438 joules. The length of the wire is just 6 centimeters, that's how much we had left. And then the heat of combustion for the wire is equal to 38 joules approximately. And then the total heat of combustion for the calorimeter, for the benzoic acid plus the wire is about 26,000 kilojoules. And using that, we can then calculate the heat of, the heat of capacitance for the calorimeter, which is just under 10,000, just under 10 kilojoules, just under 10,000 joules per Kelvin. Then you run the experiment again with the unknown fuel source. In this case, we use the Sour Jack candy. We just cut out about a gram of it. And similarly, the exact same thing happened. We watched it, or we let it approach room temperature. We had a little source of random fluke right there. But everywhere else it seemed pretty expected, pretty constant. Again, I just cut out the irrelevant parts. I brought it down. We can see that it's about 100 seconds, the entire reaction. And it's about 180 seconds, because this reaction, it got up right here, but then it also continued rising over there. And like I said, that's one little place where error can occur, because we don't know exactly where it stops. Some people might call it right here, some people might call it right there. Again, we just have a table of the results. The only thing that we didn't have from the experiment measurements is the change in temperature. That's just what I had to calculate. And after that, we can see, again, we only had 6 centimeters left of the wire. And we can calculate the heat of capacitance for the wire, which was about 38 joules. And then we can use that to calculate the total heat of capacitance, which is about 13,000 kilojoules. Then from that, we can calculate the heat of capacitance for candy, which is slightly lower, just because you have to subtract the wire contribution. So it's again about 13,000 kilojoules, about 366, or 13,366 kilojoules, sorry. And then on a per mass basis, you can calculate that just from the 1.02 grams of candy that we had, it is 13,104 joules per gram. In conclusion, we can see that the thermal capacitance of the calorimeter is 9,739 joules per Kelvin. We can see that the heat of combustion for the Sour Jack on a per mass basis is 13,104 joules per gram. And again, some possible sources of error are just where you read the graph. The system is not truly adiabatic. We kind of make the assumption that it is, and it's a good approximation for what we're doing, but it's not truly, and it provides a little bit of error. And then there's also a work input from the motor. Anytime you do anything to the system, add work, spin the water around, it is adding work. However, again, it's such a small amount that it's practically negligible. And here are just my citations.